Determining continuity by looking at a graph can be pretty straightforward. We just trace along, look for any holes or breaks, places where we'd have to pick up our pencil. But what we need are some techniques for understanding where a function's discontinuous without being given the graph. So we want to set up a few properties that'll help us answer some of these questions. So the first type of function we want to look at is f of x equals k, where k is some constant. So that would be looking at a function like f of x equals 4, y equals 3. So that's always going to be a horizontal line. So if we're talking about the graph of a horizontal line, that function's always going to be continuous. There are never going to be any holes or breaks, so the function's always defined, the limit's always going to exist, and those two values are always going to be equal to each other. So if we're dealing with a horizontal line, that function will always be continuous. Similarly, if we're dealing with a polynomial function, polynomial functions can change directions, they can have different behaviors, but they'll be defined for all values of x, meaning that, again, the limit will always exist at any point, and that'll always be equal to the function value. We don't have any holes or breaks to consider. So polynomial functions are always continuous as well. And then our third case to consider will be rational functions. So rational functions can have places where our function is undefined, which means we'll run into one of two situations. If we have a point where our function is undefined, we could have a vertical asymptote, or we could have a hole in the graph. So in either of those cases, at that asymptote, at that hole in the graph, our function will be undefined, meaning that that rational function will fail our definition for continuity. So rational functions are going to be continuous unless our function is undefined. Everywhere else, except for at those points where it's undefined, the graph is going to be smooth and continuous. The limit will equal the function value, so that definition will hold. So let's take a look at a couple of examples here. We want to determine where each of the functions below is continuous. So our first function, x to the fourth plus 2x squared plus 1. Well, this is a polynomial function. So since it's a polynomial function, using those properties we've established above, there's no work we have to do. We just know that this is going to be continuous from negative infinity to infinity for all values of x. In part B, now we've got a rational function. So we need to take that denominator, set it equal to 0, to find any points where our function would be undefined. So we could factor this as x minus 4 times x plus 1. Setting that equal to 0 would give us points of discontinuity at positive 4 and negative 1. So our function will be continuous on negative infinity to negative 1, union negative 1 to 4, union 4 to infinity. So essentially what's going to happen is we're going to have one union symbol, or break, in these intervals for each of our points of discontinuity. So we'll have a break in that continuity at x equals negative 1, and a break in our continuity at x equals 4. So then in our last example, we want to determine the continuity of x plus 1. So even though this isn't being raised to an exponent like 2, 3, 4, this is still technically a polynomial function. We could be a little bit more specific and call this a linear function. But it's still technically a polynomial. We've got it raised to the first power, even though we don't write that since it's just a little redundant. So a linear function is just a special case of a polynomial function. So if we have a linear function or a polynomial function, we know that this is continuous for all values of x. So for linear functions, for straight lines, for polynomials, that function is going to be continuous everywhere. When we have rational functions, take the denominator, set it equal to 0, and then identify those points of discontinuity.